All right, vectors. So if you've been in physics, my guess is that you've already done some stuff with vectors. And so what we do in here is really basic stuff with vectors, just starting to talk about them and learn about what they are. In general, we're going to look at representing vectors as directed line segments, right? The component form of a vector, perform basic vector operations, find the directional angles, and then solve your real life problems. So think about what problems you have, and we'll probably apply a vector to it, and it will be all set. Right? Do you guys know anyone named Vector? The guy from Despicable Me's name was Vector because he committed crimes with magnitude and direction. And we're going to learn about magnitude and direction of vectors today. All right. We should watch the movie. All right.
I thought we were going to watch a movie.
So with a vector, if you look at this, a vector is a directional line segment. So a vector has an initial point, which is where it starts. So if they talk about the initial point, that's your starting point. And it has a terminal point, that's your ending point. Right? And then the arrow would tell you what direction it's going. So the direction matters. And so if they tell you that you have vector PQ, it means it's starting at P and it's ending at Q. And so these vectors right here, if you look at these five vectors are all equivalent vectors because they all have the same magnitude. And when they talk about magnitude of a vector, that's just the length of a vector. So these vectors all have the exact same length, and they all have the same direction. Meaning if you were to draw a horizontal line underneath all of these vectors, right, if every vector got its own horizontal line, the angle between the vector and the horizontal line, every single angle would be the same. So when your magnitude is the same and your direction is the same, your vectors are equivalent regardless of where they're floating out in space. So a couple ways that vectors are written. You'll usually see them written as a lowercase letter that's bolded. Sometimes, though, you'll see them written as the initial and the terminal point with the direction arrow above it. But either one of those will tell you that you're talking about a vector. And remember, a vector is just that directional line segment. All right, so if we need to show, for example, one that two vectors are equivalent, what we're going to do is we're going to show that the vectors have the same components. Okay. And what components are, so if you look at your formula sheet, you see the first thing on your formula sheet says component form of a vector, and it has those pointy brackets and it says AB, right? So the components of a vector are your A and your B, and you get those by your initial point of your vector starting at 0, 0, and the end point of your vector would be your components. So for vector PQ, because that one already starts at 0, 0, PQ has the components of 3, 2. For vector RS, in order to find components, right, so to find component formed, so to find component form, you need to do your terminal point, right, term in L, not N, terminal minus initial. So what we're doing is we're shifting, like the vector RS, we're shifting it down to that same starting place at P. So if we do terminal minus initial, you do your terminal X minus your initial X, So we would do 4 minus 1. And then you did your terminal y minus your initial y. So 4 minus 2. So we get that the components for our S are 3, 2. And so if you think about what we did, we took this R and we shifted it down 3, so horizontally, down 2. Horizontally, we subtracted 2. And then we went, vertically subtracted 2. Horizontally, we subtracted 1. So we're just doing that shift and moving that vector down. And since they have the same components, the vectors have to be equivalent. All right, so component form of a vector. We've already talked about what component form looks like. So just as a reminder, it's when you have your brackets and you have your A and your B, or you might use an X or a Y, an X and a Y. So A and B is the same thing as the X and the Y. It's just the A is like your X coordinate. You need to make sure that you have those pointy brackets. Otherwise, it's just a point and it doesn't actually represent a vector. So you need the brackets. All right, so this is what we just talked about in the last slide in terms of standard position. So standard position is when your initial point is at 0, 0, and your terminal point is whatever the components are of your vector. So if it says standard position, that means you need to move the vector into component form. All right, and then here's kind of your slide with your formulas. So the first part right here, the component form, it gives you that formula for doing the terminal minus the initial for your X, and then the terminal minus the initial. And then they use V1 and V2. And remember, that's the same thing as your A and your B, or an X and a Y. So whatever letters make the most sense, I'm fine with you using. And then to find the magnitude of the vector, again, if you look at your formula sheets, it's that second formula you have, the square root of a squared plus b squared. So that's when I would wait to find the magnitude or the length of your vector once you have the components. So this part right here is just converting it into component form and then using the components. So this again is the square root, we could say, of a squared plus b squared, or the square root of x squared plus y squared. If the magnitude is 1, it's called a unit vector, kind of like the unit circle. It has a length of 1 or a radius of 1. And if the magnitude is 0, then it's a 0 vector. It doesn't have any magnitude or direction. All right, are we ready to find the component form of a vector? All right, so find component form and magnitude of a vector represented by the directed line segment that has the initial point 4, -7, and the terminal point -1, 5. So if we have to find the components of vector V, remember we are going to subtract terminal minus the initial. So we'll do -1 minus 4 and 5 minus a -7. So we get -5, 12 for the components. And then if we need to find the magnitude, so the magnitude has that double absolute value around it. That means your magnitude. Remember, that's your square root of your component squared. So of your a squared plus b squared, right? And these were the components a and b. So if we want to find the magnitude, we're going to do the square root. Whenever I have a negative, I don't carry it into this part, because when you square it, it's just going to be positive. So if you're typing it in and you forget to put parentheses around it when you square it, your numbers end up being off. So we get the square root of 25 plus 144, which is the square root of 169, or 13. So here's what we just did, visually, so you have an idea. If we were to graph this vector, we would go out -5, 1, 2, 3, 4, 5, and up 12, and we would have this point up here. This would be the point -5, 12. And our vector would have its initial point at the origin, and then we would draw that directional line. That's the vector that we just talked about. And if you were to make a triangle out of this vector, like we've done all last semester when we made triangles, we would know that this side is 5, -5, and this side is 12. And so if we did Pythagorean theorem, we would figure out that this side is 13, right? So the length of your vector is really just the hypotenuse if you were to make a right triangle out of your vector. So that's kind of how all of this stuff ties in with the triangles. All right, vector operations. A lot of empty slides here. Two operations that we'll talk about are scalar multiplication and vector addition. A scalar is just a number. So when they ask about a scalar, they're just talking about numbers. So numbers are scalars. So if you're multiplying a vector by a scalar, you're multiplying it just by some sort of constant or by a number. When you add two vectors, if we're adding u plus v, what you do is if you took vector u right here, and if we slid vector v up to the end of vector u, so right here, then that resultant vector from where u started to where v ends is that new vector. So that's kind of geometrically how you would add vectors. You put the initial point on one, and you connect it to the terminal point of the other, and then when you draw a new vector from the initial point to the new terminal point. So if they ask you about geometrically, that's what they're talking about. So here's how you add vectors. If you have vectors, they have to be in component form to add them, and then you just add their corresponding components. So if you're adding two vectors, you would add their x coordinates, and then you would add their y coordinates. So the hardest part is getting the components, and then you just add them. When you have to multiply by a scalar out front, just distribute that scalar in and multiply each component by that scalar. I feel like we can probably handle this, but let's practice. All right, we have two vectors, v and w. They've got the pointed brackets around them, so we already know that they have those are the components. So for a, if we want to do 2 times v, right? So for a, 2 times v would mean we do 2 times the components of v. We can distribute, so the new components would be -4, 10. Do you feel like that's easier than trig identities?
Yes.
A little bit. All right, if we want to subtract these vectors, then what we're going to do is subtract the x coordinates. So we would have 3 minus a -2, and then subtract the y coordinates, 4 minus 5. And so we have 5, -1. And then for part C, we have v, so -2, 5, plus 2w, right? So 2w, which is 3, 4. So we would have -2, 5, plus, we could distribute the 2 through, and we would get 6, 8. And then when you add those together, you should get 4, 13. All right, so here's kind of the general rules for your vector operations, just adding vectors, adding 0, multiplication. So if you're wondering, like, are you allowed to do something? I mean, it's really kind of the common sense or follows a lot of the same rules that just regular algebra does. So in example 4, we're going to find the magnitude with a scalar multiple. So for first one, for A, if we need to find the magnitude of negative u, let's first figure out what negative u equals. So negative u would mean that we're multiplying the components of u by negative 1. So we would have negative 2, 0. And then to find the magnitude, remember the magnitude is the square root of a squared plus b squared. So 2 squared plus 0 squared. So we would get 4. Right? And remember to use your formula sheet as you're starting to do these. Like, you don't have to have these formulas memorized. So keep looking at your paper and eventually I think you'll just kind of memorize them. For B, our 3v first, before we find the magnitude, let's figure out what the components are of 3v. So if we multiply, we get negative 12, 9 for the components. And then if we wanted to do the magnitude, we would do the square root of 12 squared plus 9 squared. So the square root of 144 plus 81. Which is the square root of 225. You remember your perfect squares? Root 225 is 15.
You have to put plus or minus.
Nope, we're not going to put plus or minus because we didn't take the square root of both sides. So the only time you end up with plus or minus is when you're taking the square root of both sides. But because this formula is just with a square root, then we don't add it in afterwards. Do we feel okay with part C? You want to go through it, or do you think you can handle it? Why don't you guys do it? Do it real quick on your own. All right.